Alright, so now we start with something which is called as Chinese remainder theorem. This is in continuation to the discussion that we already had with respect to the Euclidean, the Euler's theorem, the phi function, and this is extension to it, again related to the prime number itself. Now, what it actually does is, if you observe very carefully in the first line itself, the Chinese remainder theorem is used to solve a set of congruent equations with one variable but different moduli. If you observe the example given over here, this M1, M2, Mk, observe carefully the small m1, m2, mk, this forms the basis of capital M, where capital M stands as the modulo operator. What it does is that it will break up the a complicated time consuming multiplication or a modulo multiplication or modulo division into smaller segments. So if you observe, this capital M is being segmented into multiple small segments, small m1, m2 up to mk, in such a manner that the left hand side of the equation, of this congruent equation, is are all the same. So x is congruent to a1 mod of m1, then x again in the second equation, it is a2 mod of m2, like that. After that, after a certain period of time, we will observe that we will multiply all together to find out what will be capital M, or necessary calculation whenever we require it to be used. So the basic option is, if you see the last one, the significance of it, since the computational cost is proportional to the size, this is faster than working with a full modulus of M. So that's the basic trick why we are using it. So let's take an example for it, and that is mostly important. Now check this particular example. You have whatever happens, you have to find out this x, okay, in the left hand side, the x. Now if you observe that the following example is a set of three equations with three different moduli, which is given by 3, 5 and 7. Now 3, 5 and 7, this part, these are my M1, M2 and M3s. Alright, so this is my M1, M2, M3. So we are taking three such equations, so there can be k such equations also possible. And if you observe carefully, the M1, M2s and M3s are basically the three modules, all are co-prime to each other. 3, 5 and 7 are co-prime to each other. So that's another observation. Now the question is to find x. Okay, how do I find x? Now that's the part of the algorithm and that we are going to solve. But for the time being, let us assume that we know the process of x. We'll come to that, how we can solve x. But if you observe that x is equal to 23 is what is being calculated. Now how we calculate 23, I'll come to that later. But if you observe that for 23, this three equations holds true. Okay, and then what will happen, that this M1, M2, M3 that you are looking at, 3, 5 and 7, this will be multiplied together. Okay, and we will take A1, A2, A3 as well. A1 is my this is my A1, this is my A2 and this is my A3, to form the complete M, or the full moduli, okay, based on the x calculated x. So that's the basic rule, how we can find out the common x that will be common to all the congruent equations. Okay, that's the process involved with Chinese remainder theorem. Now let's see, we directly go to the solution or the algorithm involved. Please concentrate on this a little bit. So what happens here, that if you observe, as in the previous example, we had the generic, let me just write it down over here maybe. I'm just writing just to follow the previous example. So x congruent to A1 mod of M1, x congruent to A2 mod of M2, x equal to x congruent to A3 mod of M3. So these are the three equations. Just I'm writing in terms of A1, A2, A3 or M1, M2, M3. Just the same example I'm taking. Now question is, the first line you can see that's the part that find capital M, which will be nothing but the multiplication of M1, M2 up to Mk. Okay. So here if you observe, so M1, M2, M3, this will be my moduli. So we can multiply them. And based on that, we will find capital M1. This is the only important step over here. Capital M1 will be capital M divided by M1. Then capital M2 will be capital M divided by M2, and so on and so forth. You can see the second step over here. And why this is important? Because if you observe the final expression of X, remember in the previous example, or when I was showing you the example, X was coming as 23. So we are trying to find out that X element that will make those three equations to be congruent to each other. Now, the point is that last equation that you are observing, X is given by A1 multiplied by M1 multiplied by M1 inverse, which is a multiplicative inverse of M1, and it goes on, so on and so forth. Now, we have A1 already from the equation itself. We have M1, which we can calculate through the equation capital M divided by M1, small m1. So we need to find out the multiplicative inverse of M1, and then we club together each and every element. See, observe over here, there is a plus sign in between. So whatever we compute over here, plus the second one, plus the third one, up to k times, then take whole of mod of it. That's the process. Okay? So we observe, so first equation, please remember that capital M should be a combination of M1, small m1, small m2, m3, like that up to mk. Second important information, that capital M1, capital M2, capital M3 will be nothing but a fraction of, like kind of a fraction of capital M divided by small m1, capital M divided by small m2, so on and so forth. And finally, we get the final expression X, which will look like this. Alright, so let me just do one thing. I'll just try to it's a journal one. Yeah. So let me just write it down for you once. So alright, so M is given by small m1 multiplied by m2, m3. For the time being, we are considering only three equations, so let it be this. So capital M1 will be capital M by M1, M2 is capital M by M2, and M3 is capital M by M3. Let us keep it for the three moduli. Okay. So this is what we have. And also we can write that Mi, please make a note of this, into X of I is given by 1 of mod of Mi. Now what does that mean? This is basically, we are trying to find out the multiplicative inverse. So this Xi is nothing but the multiplicative inverse. Remember, the multiplicative inverse, the principle is very simpler, because we have to find out where the remainder is 1. For multiplicating the two element, the remainder should come as 1. So that's the same rule that of the multiplicative inverse. So let us take the example, this example. Okay, let us take a different example for the time being. So we'll come back to that. So suppose I have given the example X equal to, or X congruent to 1 mod of 5, and the second equation is given by 3 of mod of 7. This is the second example we are taking. We'll come back to that also, that why we got that 23, but this is just taking the first example. So X equal to 1 mod 5 and X congruent to 3 mod 7. So over here, given A1 equals 1, A2 equals 3. Alright. And we have M1 equals to 5 and M2 equals to 7. Right. So please do the first step. Given that capital M is nothing but 5 multiplied by 7, which is 35. That's how we are going to solve using Chinese remainder theorem for any given question where you have to find out what is x. Now, based on that, we can also find out m1, which will be m by m1, which is 35 divided by 5, which is 7, and m2, m divided by small m2, which is 35 divided by 7, and that is equal to 5. Right? Now we have to find out. So in that basic equation, so this is the information we have. Maybe I'll just, this is the information we have. Now what we have to find out is m1 multiplied by x1, 1 mod of m1, so 5. So the question is, if you know m, so you have 7 multiplied by some x1, which will make this equation happen. Understand? So we have to find x1. This x1 was mentioned as m1 inverse in the PPT. So find me an x1 or a multiplicative inverse to make this, to satisfy this particular equation. This is to be done using the trial and error method, nothing else. Okay, because this is not the specifically we are calculating for multiplicative inverse like we did for the Euclidean algorithm and all. Here basically trial and error method will be satisfying most of the conditions. So can you give me an x? Okay, so we have, if you consider for people again 7 into 1, what we are trying to achieve. If suppose x is 1, so 7 divided by 5, it is not 1. So 1 is not a question at all. Then if x1 is 2, then it's 14 divided by 5, that also is not equal to 1. But if it is 3, then it's 21. So 21 divided by 5, it is like quotient is 4, so the remainder is 1. Hence, we can say clearly that by trial and error method, we have found that x1 is equal to 3, or the multiplicative inverse to the m1 is 3. Similarly, try to find out m2 into x2 mod of 7. Please tell me, what is the value you are getting? M2 was 5, which we had already done over here. M2 was 5. Sir? 3 mod of? I didn't get it. What? 3 mod of 7? This was the question. Huh. Okay. Huh. Okay. Okay. So 5 into x2 mod of 7. So can you give me a value of x2 for which this satisfies? 10. 3. So same way, you just have to plug in the data and find out that for any particular value of x3, so we have this x3 as x2 as 3. Now if you go back to the PPT once again, the PPT, the final answer, the final x should be computed as a1 multiplied by m1 multiplied by the inverse of it. So x is given by, in this case, m1 multiplied by a1 multiplied by x1 plus m2 multiplied by a2 multiplied by x2 whole mod of 35. Got it? This is the final step. Now, if you consider there are 3 equations, then there will be another set of element which will be present, nothing else. So, in this case, you already have found out what is m1. So, we have 7 multiplied by 3 multiplied by 1 plus 5 multiplied by 3 multiplied by 3 mod of 35. So, the final answer, if you anyone, 31. So, what we can write at the final as a final answer, that our equation was x equal to 1 x congruent to a 1 mod of 5. So this can be written as 31 congruent to 1 mod of 5, and another equation was 3 mod of 7. So 3 mod of 7. This is the process involved with Chinese remainder theorem. Nothing else is required except that you have to find out x from a given set of congruent equations. Okay? And make sure that the individual modules are co-prime to each other. Keeping this in mind, can you do me the second one that we took as an example where we already know the answer? So I'm giving you that second option here. Let me just, so we have x congruent to 2 mod 3, x congruent to 3 mod 4, and x congruent to 1 mod 5. Suppose this is given. Question is to find x. Find x using CRT. CRT doesn't stand for cathode ray tube. Chinese remainder theorem. So please do that. All right. Take the necessary step. Here 3 equations are there. So definitely you will have 3 modules of M1, M2, M3. And along with that, take the necessary steps and find me the answer. Follow the steps and find me the answer for this. Please let me know if you are done. 23. So M should be around 60. M1 will be 60 by 3. M2 will be 60 by 4. And M3 similarly will be 12. So these are my M1, M2, M3 which are required. A1, A2, A3 we already know. So A1, A2, A3. This is my M1, M2, and M3. So finally, we have to find the inverse. Just let me know the inverses, what you have got. 2, 3, 3. Yes, correct. So for the inverses, you will get x1 as 2, x2 as 3, and x3 as 3. Correct. So the computation wise, no problem. Now you have to substitute in the basic equation x, m1, a1, x1 plus m2, a2, x2 plus m3, a3, x3. But remember to take the mod of 60. So the final answer, as per my calculation, it is coming as 11, I think. Yes, 11. Anyone, those who have completed 11, you are getting, right? Right. So this is one of the type of questions that comes from Chinese remainder theorem. I'll show you two more which are a little different to that of the same, but the process is absolutely the same. Okay, so let me just go back to that PPT once again. The answer is 11 for people who have not finished. Should I keep it, or you can check it later also, no problem. So this already we have done. Now this is the question I was talking about. Find an integer that has a remainder of 3 when divided by 7 and 13 but is divisible by 12. The question is, find an integer that has a remainder of 3 when divided by 7 and 13 but is divisible by 12. Can you try using the CRT to find the integer in the same rule? Here the equation is not given. The congruent equations are not given. That's the only trick, nothing else. The rest of the things are given over here. What will be the equations? Can anyone tell me? At least the first two I think you can assume. So x, if you are supposed to consider, so that has a remainder of 3. That means congruent in the right hand side, you will have 3. 3 of mod 7, like that. So maybe I'll just show you that. So this is what I'm talking about. So x is equal to 3 mod. See the difference. In this particular question, the equations are not given, provided to you. But in a different statement, different way, it has been arranged. So you can see the first 3 equation, 3 mod 7, then we have 3 mod 13, and the last one is 0 mod 12, because it is showing, but it is divisible by 12. So that's why the remainder is 0. So that's how the equation stands. So again, based on this, you have to follow the same process just like you did now, and you come across the final answer. That what is the answer? That is coming around 276. You can verify it also later. The steps are not provided over here, but the same steps should be given. Here like M1, if you consider capital M, that will be the multiplication of 12, 13 and 7. Then capital M1 again will be 2, 7. I think that will be only how much? What will be the value? Just tell me. Capital M, 13 into 12 into 7? Something, that one. So that capital M divided by 7 will be capital M1. Then we have M2 and M3 according. And again, you have to find out for that particular case the multiplicative inverse, and based on that arrange the equation, find what is x. Right? So this is another type for the same question. Although it is note that the equation has not been mentioned over here. Comes to the third one, another type. Should I wait for this? Should I wait for this? Hopefully all of you understood what my objective is in this question. It is not directly mentioned the equations in that way. In the previous example, we had x congruent to 3 mod 5 or something like that. So that was mentioned. But basically the 3 mod 5, that means that there is a remainder. 3 is basically the remainder. So here that part is given as a statement. So that's why 3 mod 7 indicates that it is divided by 7, the remainder is 3. So that is mentioned over here. Right? So this is another way of example. Acha. Now this is another example. Assume that we need to calculate z is equal to x plus y, where x is equal to 123 and y is equal to 334. Alright, but our system accepts only number which is less than 100. So what will be the calculated value of z? See the last answer, the z is the final answer that we are getting. But if you observe carefully here, there is again a small little trick which has been used over here in this particular question. As it is showing that the number is less than 100, you can see the mod operator over there. This is apparently three possible combinations that you can possibly have in terms of x and y to satisfy the condition. If you check the x, okay, what they did is x is equal to 123. But if you observe that it only accepts number which is less than 100. So if you observe carefully, 123, they have kept the mod as 99. Okay, because that's the maximum you can reach. The system accepts till 100. So 99 is what they have reached. Now, if you are keeping that as 99, then what will be the value of remainder keeping that 123 has been fed into the system? So if you can just see for yourself 99 plus 24, if you add, it will come as 124. So basically the meaning is this has been scaled down to come within the range of 99 or 200. So these values that you are looking at, they are being added. This is only 3 of the cases. It can be more than that as well. But this is just to prove in terms of 3, if it works, it will work for the rest as well. Am I clear with this? What is meant over here? Because the system accepts number till 100. The mod operator has been used for 99, 98, 97. It could have been 96 as well. In 96, what will be the remainder? To make it 123? 27. So if suppose the fourth equation could have been x congruent to 27 mod of 96. This could have been one of the equations. Same goes here as well for the y. Now the point is, based on this, they are making x plus y. So you can check here. The values have been given over here, x plus y. Now what they are assuming that this x plus y is basically z. Z. So now this falls a CRT problem. 3 equations are there, which can be extended to 5 equations as well. But whatever it is, for the timing, we can have 3 equations only. 3 equations we have: A1, A2, A3, M1, M2, M3, and we follow the same procedure to find out what is Z, and that will come around 457. So I have given you 3 types of question in CRT. One, in equation is directly provided to us. Second, some conditions are provided to us. Based on that, we trace back the equation. And the third one is a little different, that when we are based our mod or the modulus value to be less than 100 for a given condition for that matter, then we have to make sure that whatever the inputs we are feeding into the system, that also needs to be scaled down within the limit. So we just took the limiting condition for any modular operator, as we know that the finite value, we will always scale down to a finite value. Same way we are scaling it down to a range for which these equations are satisfied. 37? Your y is 334. Okay, so you suppose you have 34. So take this, add up this to 99 and 37. What is coming? 120. All right. 99. That's 99 into 3 plus 37. Yes. So it is satisfying, right? So basically they are arranging the equations based on whether, to keep this base to be within 100. Okay, suppose for example you take 96, the way we have taken it, 96, mod of 96. So in that case, what will be the remainder? If 334 is the calculated value, 46. So y would be 46 mod of 97, like that. So whatever the value we have, we are actually scaling it down to the mod that we have considered. So accordingly, we are scaling it down. All right? So that's how it is being done in this particular example. Any base, yeah. We can take it. This is only 3 samples we have taken, like has been given. but it can be extended. But by the time, like most of the questions which I come across, basically we have three set of equation, and that is enough for proving anything or verifying the CRT for that matter. So this is three times they have taken in that sense. 2, 3, 5 minutes? No, in that case, the point is the modulo operator as it stands at 100 over here, 100. So we have to take the maximum up to which, then we are taking it less. Like that's why 96 I'm taking, 95 also you can take. Like you can go on up to K. But the thing is, we are taking the maximum and then we are going less than one. Like that. Right? So this is all about the CRT part. Let's start with this exponential and the logarithm part a little bit, and then we'll come back and next day and we can extend a bit. This part, the logarithm, the discrete logarithm part is very useful, especially for the RSA system. You can see it's mentioned over already. The RSA crypto system, which comes in module 4, as I said, the asymmetric cryptography, the basic operation works with respect to Euclidean algorithm, a portion which again works with the discrete logarithm and with the help of the Euler's theorem. So we'll come to that RSA cryptography later, but again for that the mathematical fundamentals are the discrete logarithm. Now in case of discrete logarithm, again the problem is that this is not the conventional logarithm that we come across, but usually exponential part of it is a relatively difficult way to do for the generic group, the group of elements or the calculation wise. Okay, exponential part is difficult. That's why what we do is always you can see there the logarithm is inverse to exponential. It is used mostly as the adversary to the exponential process. So that is why exponential is not what we are going to discuss much, because it is very difficult to find certain cases, and that's why we will avoid that. We will always use the discrete logarithm and its properties to find out certain properties. In that we come across primitive roots. We'll come to that also, maybe not today, next day. And these primitive roots will play a very important role in the next segment, which is called as what we call as Euclidean geometry. Elliptical cryptography. Alright, so that is again leading to that. So in logarithm, as you can see, x equal to log of a to the power y. So how we can find it out? This is the generic method. No need to worry about this. This is more of the conventional integer arithmetic that we come across. Y equals to a to the power x mod n. But again, as it is a discrete mathematics, everything is related to mod. That's the only change. Other than that, rest of the things are almost the same thing, except that the mod operation will be used over here. But this is not the equation we are more fond of. Okay. So let us see this, how we have mentioned this. Just an example. So a to the power x mod n. Alright. X is, you can see that to solve x, we have this equation given, and now we have to find out what is y. Okay. So see this equation for that matter. This is modulo 19 operator. Okay, modulo 19. And the power, if you observe in the top axis, so over here, so this is like a to the power 0, a to the power 1, a to the power a square, a cube, a4, like that it goes on up to a to the power 18. Alright. Now, in case of all this operation, as they are digital in nature, most of the time this a will be considered as 2. As we know, the base is 2, because most of the cases, the set of elements that we are working on will be zeros and ones. So a will be mostly 2. So this particular table, if you observe, this is given as the first row. If you observe, so this is 2 to the power 1. It's like reading in this way, 2 to the power 1 mod 19. Alright. So that's how we go on. Then we have actually this one. Okay. 2 to the power 1. Then 2 square is 4. Then 2 to the power 8, then 16, like that it goes on. And you can observe that the data, that set that it belongs to, all the elements within the set is within the set of modulo 19. Because we have 0 to 1, 18 elements present. So you can observe that all the logarithmic elements will be present within the set itself. Okay. Now we go to here also, you can see this is for the 3. Okay. 3 to the power 1, 3 to the power square, like that. So this is for the third one. Again, this is 4, this is 5. And you can observe that after a certain period, like 4, 5, After a certain period, it goes on repeating itself. If you observe carefully, this is 1. 4 to the power 1, then 4 square, 4 cube, like that. After a certain period, it goes on repeating itself. So we don't need this as such to calculate. Okay, so this is called as the power of integers for a particular modulo operator. And based on that, we can find out the logarithmic table. But this is not the intended part of our discussion, because this is nothing to do with discrete logarithm for the time being. Alright? So this is where the second approach comes in, which is we will just define the discrete logarithm for the time being. To understand the concept of discrete logarithm, we should understand the properties of multiplicative group. In that, two elements are very important. One is called the order of the group, and the other one is called as order of the element. Order of the group already I think I have discussed in like previously when we were discussing the groups and field and their properties. Order of the group is what? Number of elements present in the group. But here there is another added element to it, and that is called as order of the element. So suppose there are 4 elements inside a group, then each of those elements will have a certain degrees of order. And an equation will be given to us based on which we can find out the order of individual element as well. Alright, so that gives us an indication about the process involved with respect to discrete logarithm. So we'll see that maybe in the next day's class, we don't need to go beyond this, because this involves some calculations, certain calculations. So we'll come back on next day's class and we'll start from this point onward. Okay.